All right, I failed to record the uh, hour, virtual office hour, where I went over um, the review for the test. So I'm reproducing it here. This time it's with Rev 4, the cheat sheet, and I've made corrections to I've made corrections to the cheat sheet. I noticed when we went through it during the virtual hour that I had some errors in it. So let's share the cheat sheet. I've posted this. I've sent it out as an email. This corrected Rev 4 version, and I've also put it on Canvas. As a matter of fact, it's attached to the module where this video is available to you. So let's just start with some uh, constants that you need. The K, F equals K sub E, Q, Q1, Q2 over R squared. And so the K is equal to 1 over 4 pi epsilon 0, which is equal to 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. Epsilon 0 is 8.854 times 10 to the minus 12 Coulomb squared per Newton meter squared. And then we have so epsilon 0 is the permittivity of free space. Mu sub 0 is um, the permeability of free space, and it's 4 pi times 10 to the minus 7 Tesla meters per amp. I think there's an alternate, but that's good enough. Okay, here's some summary of units used for the um, electrical uh, portion of the chapters. Current, 1 amp is equal to 1 coulomb per second. 1 watt is equal to 1 joule per second. The potential difference of 1 volt is equal to 1 joule per coulomb. The resistance, 1 ohm, is 1 volt per amp. So those will come later as we get to the electrical um, portion. And now some force formulas. So you have two charges separated by a distance r. The force between them is Ke, or 1 over 4 pi epsilon 0 of Q1, Q2 divided by r squared. Um, so force is equal to Ke, Q1, Q2 over r squared. The electric field at r distance due to a charge Q is equal to EKE Q divided by r squared. So it's just a single charge, and K, of course, is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. The electric flux is the electric field times the area. So the integral of E dot dA is equal to the Q enclosed divided by the epsilon 0. So the flux is equal to you take a Gaussian surface, it can be any shape, and you just enclose the total charge and divide by epsilon 0, you have the flux through it. So the electric potential, now moving on, the electric potential voltage at a r distance due to the charge Q is V equals 1 over 4 pi epsilon 0 times Q divided by R. Capacitance C, charge Q, and voltage V. This is the relationship between them. Capacitance is equal to the charge divided by the voltage. The total charge is equal to the capacitance times the voltage, and the voltage is equal to the charge divided by the capacitance. Okay, well, let's see. Oh, it's doing a weird transition. Um, okay, capacitors in parallel. The equivalent capacitance is just the sum of the capacitors, no matter how many you have. You have them all in parallel, you can just sum them together. Now, if they're in series, the reciprocal of C equivalent is equal to the sum of all the capacitors that are in parallel. So in order to get C equivalent, you have to take the reciprocal of that value, because it's given as 1 over C equivalent. Now, if you have two capacitors, you can use the shortcut. C equivalent is equal to C1, C2 divided by C1 plus C2. Now, RC circuits and the RC time constant. You have a resistor and a capacitor hooked up to a battery. You flip the switch, and this is the charge that you get as a function of time. It's Q max times 1 minus e to the minus t over tau, where tau is equal to RC. Is why it's called the RC time constant. And tau is when we get to 63% of the Q max. Now here's basically Ohm's law, voltage, current, and resistance equation. So V is equal to IR. I, the current, is equal to V divided by R, and the resistance is equal to V divided by the current, the voltage divided by the current. Now, power equations. Power is equal to the current times the voltage, which is also equal to I squared R. Since voltage is equal to IR, and it's also equal to V squared divided by R, since I is equal to V divided by R. So those all represent power. Now, when we have resistances in series or parallel, these the equation. Series is simply the sum of the resistors, R1 plus R2 plus however many you have, and the parallel is the reciprocal of the R equivalent is equal to the sum of the reciprocals, R1 plus 1 over R2 plus 1 over R3. I said R1, but let me repeat that. The 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus as many resistors as you have. Now, if you only have two resistors in parallel, you can use the shortcut where R equivalent is equal to R1, R2 divided by R1 plus R2. Okay. The force on a current carrying wire in a magnetic field, the force is equal to ILB sine theta. One thing I didn't put in here, if you have two wires, two current carrying wires, and they're close proximity to one another, the current is in the same direction on both, there's an attractive force between the wires. If they're inverted, there's a repulsion. They repel one another. Okay, force on a moving charge in a magnetic field. Force is equal to QVB sine theta, where Q is equal to plus or minus 1.6 times 10 to the minus 19 Coulomb, plus if it's a proton, minus if it's an electron. And the sine theta is the angle between the trajectory of the charge and the magnetic field. Okay. Okay, torque on a loop of area A in a magnetic field. I included a graph, and I didn't have it when we did the virtual office hour. But the torque is equal to N, the number of turns on the loop, times the current through the loop, times the area of the loop, times the magnetic field, times sine theta, where sine theta is the angle between the magnetic field B and the normal to the loop. The normal to the loop, it's the perpendicular vector that represents the area of the loop. So torque is equal to NIAB sine theta, where theta is this angle between the magnetic field and the normal to the loop. And you when the normal to the loop makes an angle theta with the magnetic field, the moment arm for the torque is B over 2, B divided by 2 sine theta. Just remember that you need to use the normal there. Okay, the magnetic field at a distance r from a current carrying wire. Remember, you have a wire, you have current going through it. The magnetic field will be formed by the right-hand rule, and that magnetic field at a distance r from the wire is equal to mu 0 divided by 2 pi times the current divided by the radius, where mu 0 is equal to 4 pi times 10 to the minus 7 Tesla meters per amp. So the magnetic field B is mu 0 divided by 2 pi times IR. Inductors, the current in an inductor at time t after closing the switch is the EMF divided by the resistance times 1 minus e to the minus t over tau, where tau in this case is L divided by R. For an RC time constant, it was R times capacitance. Here it's inductance divided by R. The magnetic field of a solenoid, BL is equal to mu 0 Ni, the current, where N is equal to the number of turns. So to get the magnetic field, B is equal to mu 0 N divided by L times the current. Now, sometimes the capital N divided by the L is substituted with a small n, which represents the number of turns per unit distance. All right. Okay, magnetic flux through a loop of area A. The magnetic flux phi sub B is proportional to the number of lines of B that pass through the loop. Now it's the ones that pass through the loop. So notice in the first A, the normal, that is the angle perpendicular to the plane of the loop, here it's at 90. The normal is at 90 degrees. Well, what is the cosine of 90? Well, it's 0. So phi is equal to 0. This is the equation here. Phi is equal to BA cosine theta. Here it's at 45 degrees and it's BA cosine 45. And the max is when the normal to the loop is in line with the magnetic field as shown here. So theta equals 0 in that case, and cosine of 0 is equal to 1. So that's your maximum. The cosine of theta varies from -1 to 1. So 1 is the maximum. That's your max phi sub B. So phi sub B is equal to BA in that case. Okay, transformers. The voltage of the secondary divided by the voltage of the primary is equal to the number of turns in the secondary times the number of turns in the primary. All right, inductive and capacitive reactance. Oh, you know what? I should have added a omega L. We all know that 2 pi F equals omega. So X sub L is equal to 2 pi F L equals to omega L. And X sub C is equal to 2 pi F 1 divided by 2 pi F C. So X sub C is equal to 1 divided by omega C. Now, once you get the capacitive reactance and the inductive reactance, you can calculate the impedance if you know the resistance value that's in the circuit. This is for an RLC, for a resistor, inductor, and capacitor in series in a circuit. Every time I say series circuit, it thinks I say series, so I've got to put my phone somewhere else. Okay, so the impedance is equal to the square root of R squared plus the difference between the inductive reactance and the capacitive reactance squared. So it's the square root of R squared plus X sub L minus X sub C squared. And to get the phase angle, theta is equal to the inverse tangent inverse, or arctan, of x sub L minus x sub C divided by R. Okay. Now the resonant frequency occurs when x sub L equals minus x sub C. So if you set x sub L equal to x sub C, you get 2 pi f L is equal to 1 over 2 pi f C. And if you solve for omega, which is 2 pi f, you get omega 0, the resonant frequency, is equal to the square root of 1 over LC. Now, if you want the frequency, if you don't want the angular frequency, if you just want the frequency, it's 1 over 2 pi times the square root of 1 over LC. Wavelength, lambda, and frequency f. Well, C, the speed of light is equal to the wavelength times the frequency. So therefore, the wavelength is equal to C divided by f. Conversely, the frequency is equal to C divided by the wavelength lambda. Okay, let's now we start getting into optics, where you have to know the two different types of reflection: specular reflection and diffuse reflection. Specular reflection is where you have a nice mirror and all the rays come in parallel and they leave parallel. Whereas diffuse reflection, they come in parallel, but they bounce off in all sorts of directions, and you don't get a good reflection. And the law of reflection for specular reflection says the angle of incidence is equal to the angle of reflection. Theta equals theta prime. And the angle of refraction, sine theta squared, not sine theta squared, sine of theta sub 2 is divided by sine of theta sub 1 is equal to the velocity of light in 2 divided by the velocity of light in 1. Snell's law, N1 sine theta 1 is equal to N2 sine theta 2. That gives you the angle. That's how the angles are related, given the index of refraction. And the index of refraction is equal to the speed of light in vacuum, which is 1, divided by the speed of light in the medium, which is V. And so here's a table of indices of refraction. You can see that for water, it's 1.33. For glass, we use a lot of the problems that we used, and I think a lot of the quiz questions just use 1.5, which is probably good. All right, I think this is the last page. Dispersion. The index of refraction varies with the wavelength of the light passing through the material. You can have we had an example, or I think it was a quick quiz question, which would be of crown glass, acrylic, and fused quartz, which would be the best to use for a lens, and it would be the fused quartz, because you can see the difference. The index of refraction goes from 1.46 to about 1.47, whereas with acrylic, there's a larger difference at 1.49 to almost 1.51. And for crown glass, it's again, it goes like 2 units, 1.49. I'm sorry, 1.51 to 1.53. So the fused quartz would be the best choice. So the index of refraction varies for the different media. Okay, total internal reflection, the critical angle sine theta C is equal to N2 divided by N1, for N1 is where N1 is greater than N2. This is the critical angle, is what we use in fiber optics. Um, okay, the mirror equation and the thin lens equation is 1 over P plus 1 over Q equals 1 over F, where F is the focal point, and the focal point is the radius of curvature divided by 2. So if you have a 20 millimeter radius of curvature, the focal length is 10 millimeters. Okay, magnification. The magnification is H prime over H, which is equal to minus Q over P. So if you know the object distance and the image distance, it's minus the image distance divided by the object distance. Now, sometimes the image may be negative if it's on the front side of the lens surface or the mirror surface. It works for either one. And I think that's it for the review. I'll post this. I think it's already posted. I may change it to where I put I put these as x of L is equal to omega L, which is equal to 2 pi FL, and omega C is equal to 1 over omega C, which is equal to 1 over 2 pi FC. Okay, I think that's it for the review. The test will be Monday night, probably like from 6 to 9. And I hope you do well.